At this stage in the activity, I'd like to review the idea of drawing a full Lewis structure. I'd like to present a systematic way. There are some rules that will guide you. That said, after some time you're going to recognize some common modalities in organic chemistry structures, and you will probably take a shortcut to get to the actual final Lewis structure or bind line drawing. But here, as I say, I will show you a systematic way. So we're asked to draw the Lewis structure for the propionate ion. To do this, number one, you have to make sure that you use up all the valence electrons. So we need to know what are the total number of valence electrons. It might be helpful to rewrite this condensed structural formula into a molecular formula so that we can more easily count the number of valence electrons. So I have C3, H5, O2, negative. Each carbon has 4 valence electrons, so 3 times 4 is 12. Each hydrogen has 1 valence electron, so that's 5. Each oxygen has 6 valence electrons, so that's 12. And then I add 1 valence electron because of the negative charge. So 12 plus 12 is 24, plus 5, 29 plus 1 will give us 30 valence electrons. We need to make sure that we account for all of the valence electrons. So total valence electrons equals 30. The next step is to make a skeleton. Now we will do some work on this, but this condensed structural formula actually gives us a hint about the skeleton of the Lewis structure. So in the Lewis structure, we show all the atoms. We also show all the lone pairs. So you may remember in the previous example where we were indicating the formal charges, those technically were not full Lewis structures because I wasn't showing all the carbons and all the hydrogens. Now I can see that I've got a CH3 group, and the bonding pattern has to be such that this is a terminal carbon with 3 hydrogens. Then I've got a CH2 group, and then I've got a carbon that apparently is making some bonds to oxygen. The most likely pattern would be the carbon is making 1 bond to 1 oxygen and another bond to another oxygen. Now that I've done this, what I'm going to do is, in terms of step 3, and I might need to come back to step 2, but in terms of step 3, what I want to do is figure out how many lone pairs I need to put into the structure. So to do this, I look at the total number of valence electrons minus the number of bonding pair electrons. So in this particular case, I had 30 valence electrons minus, and bonding pair, I count up all the electrons, not the total number of bonding pairs, but the number of electrons that are in bonding pairs. So I see 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have a total of 18 bonding pair electrons. So of course this will equal 12 lone pair electrons that I need to apply to the structure. So I start applying those lone pairs. So 6 electrons here, 6 electrons here. Oh, I notice that the carbon in the middle between the 2 oxygens doesn't have an octet. This isn't good. We want to, if we can, have all of our atoms have an octet, especially if there's no carbocation charge that's apparent. So what I'll do is I'm going to go back to my skeleton and improve on that so that the carbon has an octet. One of the ways to envision this is if one of the lone pairs were to come in here and to form another bond. In other words, there'd be a carbon double bond oxygen. So let's draw a new Lewis structure. Now what you might want to do is just erase or correct your current Lewis structure, but I find it helpful to see the progression. So I'm going to draw in these hydrogens. Now carbon double bond oxygen to another oxygen. And at this stage I'm going to do another calculation. How many lone pairs do I need? Well, 30 minus the bonding pair. Well, now actually I have 20 electrons. as part of the bonding pairs. So when I said 30 minus the bonding pair, I'm 30 minus the electrons in bonding pairs. So here we have 10 electrons that are involved in lone pairs, and let's apply those. So I'm going to add 6 electrons down here and 4 electrons over here. Ah, yes, I've used up those 10 electrons. Now I know I've used the correct number of valence electrons. The last thing that you need to do is check for formal charges, because you may remember that it's not correct to draw a Lewis structure without the correct formal charges. Very quickly, you may notice that this oxygen down here is not making 2 bonds. It owns 7 valence electrons. Neutral oxygen only owns 6 valence electrons, so it has a negative formal charge. You may also notice that in fact we can draw a second structure. Now we're going to draw a resonance form. Over the next couple of weeks, I will give you more and more practice in recognizing when you should be drawing resonance forms. Well, this is a very good case in point. It's also possible for the bottom oxygen to be involved in a double bond and the top oxygen to have a negative formal charge. So the actual representation should show both of these. And it's not, again, that the two structures are oscillating, but rather the actual structure is a fusion of both of these structures. Now, that has some interesting consequences, because even though I said, and actually I think what I'm going to do is redraw those lone pairs because they're looking kind of ugly. So there, there, and there, and now I add my negative formal charge. I said, for instance, that there was a double bond at the top here, right here. And then we talk about a double bond down here. But if the actual structure is a fusion of both of these resonance forms, there isn't actually a full double bond in any one spot. That in fact, the electrons that are in that double bond are being shared both across the bottom oxygen and the top oxygen. The actual structure is a fusion of both of these structures. Again, we'll say more about this as we move further along. But rather than refer to the fact that there's a double bond at the top oxygen and a single bond in the bottom oxygen, we would essentially say that effectively there's 1.5 bonds associated with each of these set of bonds. So 1.5 bonds there, and 1.5 bonds there, and 1.5 bonds there. Let's move on to one last example associated with this chem activity. At this stage, I ask you to draw the Lewis structure for ozone. So you're going to put into practice those steps. So I ask you to apply the systematic approach. Step 1, total number of valence electrons. Step 2, draw a skeleton. Step 3, determine the number of lone pairs. And then check for formal charges. Again, it may be an iterative process. That is, you might need to go back. Okay, so let's see how this looks. So first of all, our ozone. Now in terms of the total number of valence electrons, this is pretty easy. Total number of valence electrons will simply be 6 times 3. So that's a total, of course, of 18 valence electrons. So that was step 1. Step 2, I'm going to make a skeleton. Skeleton's pretty easy to make as well because I'm just joining 3 atoms. Step 3, I consider the number of lone pairs. So lone pairs will be the 18 valence electrons minus the number of electrons that are involved in the bonding pairs. So I can see that I've got 1 bonding pair, 2 bonding pairs, so that's a total of 4 electrons. So therefore this would equal 14 electrons. So now let's try to put out those 14 electrons. So I put 6 electrons on this terminal oxygen, 6 electrons on this other terminal oxygen. As a matter of practice, it's better to put electrons on the terminal atoms, and then we'll put the rest of the electrons in the central atoms. So I've just used 12 electrons. I only have another pair to add. I got a problem. The central oxygen doesn't have an octet. Okay, so I'm going to draw a new skeleton. The new skeleton essentially is going to take one of these lone pairs and make a double bond. And thereby, all of the oxygens will have an octet. So this original oxygen is going to be the same. And then a double bond here. Of course, this oxygen on the right-hand side will have fewer lone pairs. Now, just as a matter of practice, I go lone pair is equal to 18 minus 6 electrons that are in bonding pairs. So, of course, this gives me 12 electrons. And if I count the number of lone pair electrons I put out, it's a total of 12. Okay, so I've used the correct number of valence electrons. Now, you may have noticed that actually there's a resonance form that I can draw for this, in that the double bond doesn't have to just exist on the right-hand side. It can also exist on the left-hand side. So I make my skeleton again. I'll draw the double bond on the left-hand side, put in 2 lone pairs, 1 lone pair here, and over here I'll put in 3 lone pairs. Of course, step number 4 is to check for the formal charges. The oxygen right here has a negative formal charge, as that oxygen owns 7 valence electrons. The oxygen in the middle here has a +1 formal charge, and the oxygen on the right-hand side has 0 formal charge. Again, in terms of the right-hand resonance form, plus here and negative here. So this leads to an interesting conclusion that, again, although we talk about a double bond between the oxygen, there in fact is no double bond, because the electrons, and here's a new word that we haven't talked about, are delocalized. Those electrons, which we will be talking about, pi electrons, exist between the oxygens on the right and on the oxygens on the left. And so once again, instead of having a single bond and a double bond, we're talking about 1.5 bonds and 1.5 bonds, 1.5 bonds and 1.5 bonds. The actual structure is a fusion of both of these resonance forms. Now I've got a nicer representation of these Lewis structures right here. So hopefully you feel some confidence in drawing the Lewis structures and having some strategy. Just as a last point, let's look at this table here. Now, one of the ways that we actually know that drawing 2 resonance forms to represent ozone, or drawing 2 resonance forms to represent the carboxylate anion, is if we check out bond length data, the resonance forms are more consistent with what is actually happening. So a typical oxygen-oxygen single bond has a bond length of 1.48 times 10 to the negative 10 meters. A typical double bond has a bond length of 1.21 times 10 to the negative 10 meters. Experimentally, in ozone, we find that the bond lengths are identical on either side. So again, there's not an actual double bond, there's not an actual single bond. And note that the bond length is intermediate between a single bond and a double bond length. If we talk about the bond order, which is in effect the actual number of bonds holding together 2 atoms, instead of talking about 1 or 2, we can say that there are effectively 1.5 bonds. So what I was writing before, we can call the bond order. And then finally, effectively, there are 3 electrons per bond. This ends, for now, the chem activity number 1. We will do some more practice together when we convene.